microphone. All right, welcome everybody this morning. It's a pleasure to have Michele Governale give us a talk this morning. Michele has got his PhD at Pisa, University of Pisa, I believe, and is now a professor at the Victoria University of Wellington, and an investigator in the McDermott Institute, which is one of our partner organizations in Fleet. So it's nice to have him visiting us here, and he is going to tell us today about boundary states and corner states in topological insulators.
Thank you very much for the introduction and for the invitation to present here. And today I'll share with you some very recent work, and let's see how we're doing with time. Some of at the end, there will be stuff that is actually really ongoing where we are actually working on. So there will be a very brief introduction. I think I am in a sort of venue where probably the introduction is not that much needed, and so I will keep it really brief. And then in the next part, I will talk about second-order topological insulators, and basically I will introduce some analytical calculations on sort of the boundary states, on the corner states of this second-order 2D second-order topological insulators. And then the last part is looking at electronic transport through this second-order topological insulator flakes, and we will see whether we can make devices that look like switches and which sort of are protected by topology. So that's the plan. Usually I like to acknowledge people I work with from the beginning, because at the end maybe I will always run out of time. So here these are people that I've worked on topological materials. People like Uli Zulige, also from the McDermott and Victoria University, Jared from RMIT, and a few others. But the people in red, Fabio Taddei and Joe Poata, are actually those who have been heavily involved with the work that I will present today. So Fabio is a long-term collaborator from Scuola Normale Superiore in Pisa, in Italy, and also a very good friend. And Joe is a master's student at Victoria University of Wellington, and is currently working on these things. Okay, so topological insulators in a nutshell. So these are materials that are insulating in the bulk. So, nothing strange. But if you have a boundary between a topological insulator and, let's say, vacuum or something that something normal, then you have on the boundary you have conducting states. And so, for example, if you have a three-dimensional topological insulator, then you basically have this chunk of topological insulator. Then if you look at the surface is 2D. And if you look at the excitations on the surface, there are basically gapless Dirac cones shown here. So the excitations have a linear in-plane momentum. So if you instead look at 2D topological insulators, then here the boundary states are 1D, and these are these 1D helical edge states of the quantum spin-Hall effect. So people, when talking about topological insulator, they often refer to this bulk boundary correspondence. And basically, if you have a d-dimensional topological insulator, then there is a grammar mistake here. Hosts gapless boundary states in d-1 dimensions. So if you have a 3D, then you have 2D boundary states. If you have 2D, you have 1D edge states, and so on and so forth. So let's, when talking about topological insulator, I really like this to introduce what a topological insulator is and how it works and why it's topological. I really like this example, which is basically bismuth selenide. And here we have somehow on the left, we have the crystal structure. It's complicated. I don't want to focus on this. I want to focus on this right panel. And so the right panel basically shows how you can somehow get an effective model for bismuth selenide. And so you start with orbitals, with p orbitals on the selenium atom and bismuth atom. And here, this would be like when they don't hybridize, that would be, so to speak, the sort of atomic limit of a, where basically you don't allow the orbitals to hybridize to each other. So you have no chemical bonding. But then, as a theorist, you can start sort of, and then say, okay, now let's see what happens if they hybridize. And then what happens is that, the state change in energies, and you have these p states here, which you call p plus and p minus. You could imagine them as kind of bonding and anti-bonding states, and similarly for these ones. And this still would be, so to speak, the order that you would have in a sort of trivial insulator. And then you allow for the crystal field, and that causes these states here, the P1 plus and the P2 minus. So where plus and minus refer to parity here, but it's not too important. They still split. So they split, and so now, you have they were degenerate in X, Y, Z, and now they split. And but still the order is basically the same as in the trivial case. But then, and that's the pleasure of being a theorist, you can sort of, add pieces to the Hamiltonian one by one, which is a luxury that, of course, experimentalists don't have. And so if you add spin-orbit coupling, then what you find is that basically this, you see these states invert in order. We say that basically the gap changes sign, and that's the topological state. And then you can, of course, create, if you're interested only in energies around the Fermi energy, so a low energy model, you can sort of consider these, let's say, these 4 states as basis states and create an effective model. And this is the so-called effective BHZ model. And if you start with this, then you can sort of, you can, for example, model a finite system, and you will find the surface states that we were talking about before. Okay, so what are higher order topological insulators? I'm sorry that I'm sure that this introduction was a bit boring for people here who are all, but now maybe not everyone is familiar with higher order topological insulators. So if we have, so to speak, the standard, let's say vanilla type topological insulator in 3D, we basically have surface states that are 2D. Now, if I have a second order topological insulator, then what happens is that the surface states are 1D, and in this case are called hinge states. So because basically they live along the hinges of this system. If I have a third order topological insulator, that's the highest one that I can have for a 3D system, then basically my surface states, become corner states. So I just have states at the corner of the system. And so in principle, what we can say, we can sort of introduce a generalized bulk boundary correspondence, where now my d-dimensional nth order topological insulator hosts the same grammar mistake, gapless boundary states in d minus n dimensions. So 3D, if I have a second order topological insulator, so 3 minus 2, I have 1D boundary states, the hinge states. 3 minus 3, I get the corner states. And so to speak, our vanilla topological insulator, things like bismuth selenide, is basically a first order topological insulator in this categorization. Okay. How can we, so now I will focus on a 2D, two-dimensional, so like second order topological insulator, and I will shorten it as SOTI, just for short. And
may I interrupt you and ask a question?
Yeah, of course.
This is, let me consider two-dimensional, right? Two-dimensional topological insulator.
Yes.
And I want to consider second order, right? Second order two-dimensional. Then you say that in corners are effectively quantum dots. Correct?
So basically there would be states that are localized at the corners.
At the corners, correct. Good. So 4 corners. So if I have a square geometry, I have 4 corners. Then I have 2 questions.
Okay. Yep.
First question: first question: what is the direction of the spin of these states in the corners? And second question: if I make a two-dimensional sample without corners, it's a circle.
Okay. Can I interrupt you?
Yeah.
Because, okay, so the first question is what the spin, it depends actually really on the model. There are different models of second order topological insulators with different symmetries, and I will talk about 2 models. So, and I will answer that question. Whether you will, the other thing is whether you will have states again at all corners or not at all corners, that will again depend on the model and the symmetries of the model. And actually, we will also see what happens if you don't have corners. So what I will suggest is that I'll go ahead, because I think the first part of the talk will answer basically all your questions.
Okay, thank you.
And if I haven't answered all your questions,
okay,
you stop me, and I'll be happy to somehow try to answer what I haven't.
Please go ahead.
Okay, so I will use as a model which is done by one piece that is, so to speak, a vanilla topological insulator in 2D, plus an extra term that, and the effect of this extra term will basically to gap the edge states, so that the edge states will not exist anymore, and instead we will get corner states. And so let's first focus on this first part. This first part is basically the equivalent of the BHZ model in 2D. It's written slightly differently, but it's basically unitary equivalent. So there is so here we have, so it's a 4x4 model. And so we have Pauli matrices sigma and tau. And the degree of freedom described by sigma could be its spin, let's say. And tau is some other pseudo spin, some orbital degree of freedom, which orbital we are in. So we have one term here that is, so to speak, diagonal, and it has the gap M0 plus a quadratic term, which it's important to somehow regularize the theory. And then we have a term that mixes momentum and spin, so it's like a spin-orbit coupling, and it's term of this form. So if I look at this model and I consider, I just consider this model here, the topological insulator model, and I look at what happens at an edge. So I consider semi-infinite system and I have an edge. And then of course what happens is that I can define an effective Hamiltonian for the edge, and surprise, surprise, I get the linear states in where K is momentum parallel to the edge. So that's somehow a sanity check, and that's what you get. And then so now let's focus on the extra on these terms here, and I have considered two cases. And the reason for this is that one is extremely simple. This is this one. And if you look at the form of this thing, it's sigma x plus sigma y, tau z. So it looks like it's like a Zeeman field along the direction, basically 45, the making 45 an angle of 45 degrees with the x-axis along this direction here. And you see it acts as tau zero on the orbital subspace. So that's very simple. And that's actually has been discussed already in the literature. And the next one is a bit more complicated and has actually some shows actually some richer physics a little bit due to the momentum structure here. And that was one of the first topological insulators, this second-order topological insulator described by Schindler and co-workers So that's the second one. And basically, model one has inversion symmetry. Of course, it breaks time reversal symmetry. Model two has a combined symmetry as C4, so rotation by pi over 2, and time reversal symmetry. So it breaks each individual symmetry, but if you do both, this symmetry is conserved. So okay, so these are the two models that we will use, and now for just as a remark. So there are people who classify Hamiltonian with this Cartan classes, and so based on symmetries, and it's not too important, but just the idea is that these both models are in this Cartan class called A3, and basically what it means is that the time reversal symmetry is broken, particle hole symmetry, so charge conjugation symmetry is broken, but there is something that is called like a lattice symmetry, or sometimes it's called also chiral antisymmetry. Basically, there is an operator that anti-commutes with the Hamiltonian. And in this case, is this particular combination of sigma z and tau x. Okay, so we have these models, and somehow it has been a bit mathematical so far. And now let's try to understand how we get corner states. Yeah. So, okay, so if you don't have this term, what you will find is that you will have the linear dispersing states within the gap, and then if you make a flake, so if you make an infinite system, you just have the gap and zero, and states above and below the gap. If you make a finite system, let's say a square flake, then you still have the gap, but then you have this linear states inside the gap. Then now if you add this term, we will see what happens to those. So those they still have the gap, but those linear dispersing states basically disappear, and you have, well, what you have is you on top of this you have excitations in the center of the gap, so to speak. In this model would be at zero energy in the center of the gap, which are localized. So that's these corner states.
So it's usually constructed to plot the Berry curvature for the land structure. Usual topological states.
Yes.
They correspond to the
non-zero
flux of the Berry.
Yeah.
What happens with the Berry curvature if these additional terms are present?
So yeah, I haven't done this, but so because obviously the topological insulator part gives the standard Berry flux. Yeah, that's a very good question, and I need to sort of, I don't want to give you a rushed answer that might be wrong. But people have defined basically topological indices for these things. So anyhow, but let me show how those terms lead to the corner states in an actually very natural way that I think that will also then give us more insight on properties of those corner states. So I'm going to do something that is very trivial. So I start with my system here, my SOTI, second order topological insulator. And what I want to do is I want to do a rotation of coordinates in a coordinate system where I have an axis parallel to an edge, to the edge. So I'm considering one edge, and the other axis perpendicular and pointing out. And so that's, trivially how this coordinate transformation is defined. And basically we can take this rotation angle, the rotation that I need to do to get from the coordinate system in black to the coordinate system in red, as the angle that defines the direction of the edge. Okay, so that's it. That's we have this coordinate transformation. That's sort of a kind of trivial task. We do that, and we get transformed Hamiltonians, and of course, these linear terms these terms in K, the linear terms in K will acquire, dependence on this angle alpha and so on and so forth. And so that's not too important. We can do that, and I just wrote them here, but I don't expect you to sort of look at them too much. And I want more to explain what is the gist of what we're doing. And then you can say, okay, now let's take the term that introduces the terms basically that introduce the gap for the edge states, this HM, and let's for now take it to zero. Also, let's consider the case where my momentum parallel to the edge is zero, so to speak. Along the edge, I am basically at the gamma point. And then if this term is zero, then what I have is I have back my vanilla topological insulator. So I redo the calculation, but that basically I have states shown here which have some linear combinations of the basis states. So here this one is referring to tau, so to the orbital, and this is the spin, and plus it has some transverse profile, and this transverse profile is exactly the one for the topological for the vanilla topological insulator. It's something like this, that it looks it's localized along the edge, and the decay length here is set by a characteristic length scale that depends on the basically this spin orbit coupling constant A and the gap M0. So it's this R0 is the natural length scale for the topological insulator. And this edge state is localized within a few R0 from the edge. That's all known. So that's not nothing, that's basically all, it's all an old story, but I just need to basically define you these states here, phi 1 and phi 2. And so, but that's basically an old calculation that, you know, has been done like, I don't know, 10 years ago or whatever, on topological insulators. So now what we do is, now we include, we take matrix elements of the terms that are linear in K parallel, and this term here, the HM, in this basis here. And then, of course, what we find that, let's say that still HM is 0, but then we find the effective Hamiltonian for an edge of a topological insulator with the linear terms on the diagonal. But what we find is that this term, as I was already telling you, introduces here off diagonal elements, so it basically gaps the spectrum. And these matrix elements, this M, this induced mass, depend on the model. For model 1, the one where it was a magnetic field, it's basically has this direction, and depends also on the direction of the edge. So it depends on alpha with respect to the direction pi over 4, which was the direction in which this sort of Zeeman field was. So this is this M1, and it's basically shown in blue here as a function of the edge. So, and M2 again depends on the direction on the edge with respect to the crystal axis, and it has a bit of a more complicated dependence on the direction of the edge. So, and this lambda plus, it's something that just contains, it was defined before. It just contains the parameters of the material. Okay, so basically, so this model, this is the effective Hamiltonian for the edge, and basically it explains how this term here introduces basically a gap in the linear spectrum. And then what we can do is we can go further and we can consider two edges, and then we can ask ourselves, do we have a corner state there? And then the answer is, we do have a corner state if the induced mass on edge 1 and edge 2 have different signs. So basically we are at the, if they have different signs with basic signs, basically what we have is we have two different, it's like two different topologies, and then we expect a boundary state. And because basically we have band inversion here. And that's and so that's actually works pretty well. And what I've done here, for model 1, yep.
Think about like the domain hole. There's this less slowly changes this.
And I will answer, yes, you don't need a corner. In fact, you don't need a corner. And if that was, so this is actually answering also, I think it was Oleg in the ether. I couldn't see him, but
yes, it was me.
It sounded like Oleg. So this is also Oleg question. No, and in fact, it was actually one of my curiosity was like, what happens if I have a circle? And where do I have corner states? I have no corner. And I think the name corner state, in a way, it's a little bit misleading, because in a circle, basically the mass would change sign continuously, and you still will have a state where it changes sign, and we will see it. So okay, I first started with a triangle. And this is model 1, and I want to show you a few things that this model even is so simple, but it's already giving you some information. First of all, it will tell you that along one edge, the corner state will decay with a characteristic length scale, which is now the parameter A, basically the velocity of the linear modes, divided by the induced mass. So, for example, in this case, here I have some written in the values of the induced masses on the different edges. So here, the induced mass has an absolute value which is smaller. So I expect that my corner state, which is here, will decay lower along this edge, and you already see it. And on this edge here, the induced mass has a larger absolute value. And so here, the corner state decays much faster. I can also have situations, and so this is a bit of a special case in which the effective mass, so this edge here is exactly at 45 degrees, and the effective mass vanishes. And so your corner state, it's actually, extends along this edge. So in this model, and so you see that this kind of very simple model will tell you also about the localization, how localized are those corner states, how quickly they decay along an edge, and also, it predicts that there are these situations where the state extends along an entire edge, and then we can play a little bit, and I'll go fast on this because basically we can look at whether we can sort of try to verify our prediction by doing some numerics using a finite difference method, and so using basically discretizing the continuous model on a lattice. Here, what is important is that this lattice parameter has to be smaller than this R0, and that's when you are in this regime, usually it's a very good description. And so this will basically corroborate our findings, but also maybe also give us a little bit of information when we look at probability densities and stuff like this. So if you look at the model 1, basically the one with inversion symmetry, you find that for flakes in the shape of a convex polygon, you always somehow the geometry works in such a way that you always have two corner states, positive, so positive mass, negative, negative, so corner state here and here. Let's say that you rotate the polygon, you still have you still have two corner states. This is the case in which one is extended. You keep rotating it. You still have two corner states. You have moved them. Here they were at the basis of the triangle. Here one at the basis and one at the apex. But so you can change the positions. You can change how much they extend by cutting the flake in a different way with respect to the magnetic field or crystal axis, but you cannot change the number. And then, of course, you can play and say, oh, look what happens if you have a square. Again, you can have, you'll have always two, but you can also have extended ones. So to answer one of the question of Oleg, with this model, with this symmetry, if you have convex polygon, you always end up with two corner states, which are basically defined by where the effective mass vanishes. And then again, to go back to the original question, is what happens if you have something like a circle, and what happens is that you still have two corner states at basically at zero energy, and they are located along this. So basically, the magnetic field is in this direction, and they are located here, and here. And you can see this in principle. You can imagine that the circle is like a limit of a regular polygon when the number of sides goes to goes to infinity, and you see, so here we did, I don't know, I don't remember how many sites we did. Is it octagon? And you see that you know there are only two corners where the mass change sign. Okay, so so I hope that this answer at least some of the questions. Yep. So yes, I think if it is not convex, I think you will end up with more states, and we basically stopped because somehow it felt like we were now, you know, sort of really. So yes, we can do convex, then we can do convex. Now we do concave, and so somehow we went a slightly different direction. But yes, you get actually we did look at some shapes, and of course you get some. I think you can get more than two. You can get. Is it going like this? Yeah. Yes, it is. Yeah. Yes, it is. Okay. So
Michele, may I ask a question?
Yeah.
Can you show previous with circle? This left panel, when you have a circle. This is a model 1, which is time mode, right? So it implies that magnetic field is directed. What are directions of the spins on these spots?
So I think it's going to be, because you see those states are going to be something, a mixture of this. So it's going to be a mixture. So in this case, basically is like pi over 4. Alpha is like pi over 3/4 pi over 4. So it's going to be, technically it is like a mixture of up and down, but with different also plus and minuses. So if you actually if you only take, so to speak, the expectation value of spin tensor product tau 0, you end up with 0, but it will be something like sigma x cross tau x that will have a finite expectation value. So it's so basically, yes, we have. So basically, we have the state, and we have the state, and we can calculate the expectation value, of spin. I think the answer is that is not is a linear combination of because it's in a 4x4 model of the orbital pseudo spin and the spin.
But anyway, other spins on these spots are opposite?
Answer. Yeah.
It's opposite. Say left is up and right is down, right? And in another valley, it's other side around, right?
Sorry. Mean left, this one is up, this one is
down. Say up, whatever is up means, but yeah.
But it's a bit of a more complicated structure, just not because it has it's a linear combination, not also states with different orbitals, so with different taus.
I am asking because can I make a sort of imagine that I adiabatically change direction of magnetic field. What happens?
What happens is that they move, and their spin structure will move. So if you change adiabatically the direction of magnetic field, these two states. So let's say in this case the magnetic field is along this direction. Okay. If you adiabatically move it, you basically move them around, and you change their structure in sigma and tau.
Interesting. Okay. Okay.
It is interesting, and we'll see. Actually, that's a very good point. Will bring us to the next part of the talk.
Thank you.
So for the second model, it's actually interesting that basically the number of corner states, it can be 0, it can be 2, it can be 4, not for a triangle, of course, but for something else, for a square, for example. And so here I've shown one case in which here you have two of the induced effective masses that are negative and one that is positive. And so here you see your corner states. And then this state here, and so this energy is basically at the center of the gap, as we expect for this type of excitations. So here, this is basically the spectrum. So the gap is in blue. And if you rotate this, you can create, since there is this dependence on the direction alpha is actually 2 cosine of 2 alpha, you can create a situation in which all the masses are negative. And then what happens is that actually, if you look at the spectrum, you have killed the corner states. And yes, and so what I'm showing here, so I didn't want to show simply a white triangle. So what I'm showing here is the lowest energy states, which actually is here. It's quite high. So that's not a corner state. It's not topologically protected. And so you can create situations in which, for this system, in which you have 0 corner states. Sorry, I didn't show for the square. You have for the square you have actually 4 corner states in this model. I haven't shown this because the reason why I didn't is because I wanted to save a little bit of time to It doesn't. Yeah.
For the left here, do we expect to have a pair of states at each corner, 2 corners, and if the states overlap, they could hybridize and they could split into 2 states.
Yes, yes, that's correct. That's correct. That's similar to, yes, that's correct. So okay, so now the idea is, can we use some of the information that we have learned? And basically, it's a little bit of the Oleg idea of rotating that magnetic field. And so now what we consider is very similar model to what was before. So we have this flake here of second-order topological insulator. And now I'm considering only the model with the magnetic field. But now, instead of considering a fixed direction, I can change the direction of the magnetic field. And that's defined by the angle theta. And the idea is that, for example, if my magnetic field is like this, then I have corner state here and corner state there. And then this will be localized here and here, and I shouldn't have transport. But if my magnetic field is like this, is along the x-axis, then I should have an extended state along this edge, and then I should turn on transport between 1 and 3, but not between 1 and 2. And if my magnetic field is like perpendicular along the y-axis, then I expect an extended state here along edge 2, and then I should enable transport here, but not here. So it's kind of cool. And so, and for the leads, we just consider basically a topological insulator without B. So let's start with the simplest problem before doing the 3-terminal setup, which is the 2-terminal setup. So this should be on and off. When I have an extended edge, horizontal extended edge. So for the magnetic field along 0, theta equals 0 along the x-axis, I should have an extended edge here. And if B is along the y-axis, on the other hand, the extended edge is here, and I should not have any any transport between lead 1 and 2, and so on and so forth. And now it turns out that if the Fermi energy is much smaller than M0, you can basically find an analytical model. And let's say that the Zeeman energy omega z also introduces a length scale, Lz, which is the velocity of the linear excitation divided by omega z. Omega z is this just the scale of the Zeeman energy. And if you, in this limit, you can actually solve this by mode matching and get all the transport coefficient. Analytically, I'm only showing them at 0 Fermi energy here, the formula, because the other one is a bit bigger. In this case, basically depends only on theta and this relation between the length of the edge and Lz. And so these are plots. So for Fermi energy equals 0, you have a peak in transmission when at 0, of course a pi, and the transmission goes to 0 when the magnetic field is along y, as expected. And this one, it's a very good description as long as E Fermi is much lesser than M0. And basically, we have done the numerics. If E Fermi is, let's say, of order 1/10 of M0, the numerics is completely on top of the analytics. And we also have introduced disorder. And of course, this mechanism is robust against disorder because when you have transmission, you basically have, it's like a topological, you basically reconstruct the topological edge here. And that's robust with disorder. So we have introduced disorder and it's robust. And if you make longer devices, so L over Lz is larger. For E Fermi equals 0, you just still see the peak. But for E Fermi different than 0, you see basically these are mesoscopic 5B/ρ oscillations between the two. And the numerics confirms all of this. And when you introduce disorder, the peak is preserved, and these oscillations are affected. So that's kind of super cool. And then the next thing that we checked is what happens with the 3-terminal devices. Again, we can get analytic expressions for E Fermi much smaller than M0. And in this case, we expect, as we said, for example, if the angle theta is 0, we expect that we have transmission between 1 and 3. And so G13 goes to 1 at 0 and a pi. And on the other hand, when the magnetic theta is equal pi over 2, then we connect 1 and 2, and the G12 goes to 1 here. The width is set by the scale L over Lz, and here you see that L vertical is different than L horizontal, and that explains the different peaks. We expect that these oscillations will, this behavior will be robust against disorder. The simulations are currently running, so that's an expectation. So here I'm just being optimistic, but I don't see why it should work differently than the terminal one. Okay, so I'm conscious of the time. So I just presented to basically second-order topological insulator Hamiltonian, both in the same sort of Cartan class. And the idea was to give a simple explanation on how these corner states occur by sort of getting this effective Hamiltonian for edges. And this is not only one nice way of seeing how this effect comes about, but it also gives you a little bit of insight on what is the decay length of those corner states. And so we could play with this, and therefore we could somehow with model 1, we could show how this position of the corner states and decay length can be controlled. And then that allowed us this kind of proposal of topological switches. Thank you so much for your attention. And Oleg, I hope I answer your question.
Yeah, thank you. May I have another question, please?
Oh, of course.
So you explain about your model 1. What will happen for model 2? Because model 2 is probably relatively easy to realize with gallium arsenide, holes with gallium arsenide. What happens with at the level of scenario? How states look for model 2? For example, if you have a round, well, anyway, a model 2.
For model 2, for example, in model 2, unfortunately, I couldn't use my Mac because it was a hidden slide on my Mac, but this is now a PDF. But let's say model 2, if I take the circle of the circle for model 2, I would get states here, 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 and here. Because basically, because you see that the mass, there are 4 directions in which the mass goes to 0, between 0 and 2 pi.
You get 4 quantum dots, and in each dot is double spin degenerate, right?
No, I think there will be I think that you'll get 2 pairs. So I think you get you only get 4 states. So each dot has whatever combination of spin and orbital.
But your Hamiltonian was spin independent, was it?
No.
Additional.
The Hamiltonian, you see, if you look, the Hamiltonian, where is it? Here. Yes, it's spin independent, but tau mixes tau y. But then this term mixes spin and spin and tau as well. So I'm pretty sure you only get 4 states at low energy.
Okay. Okay. Thank you.
You're welcome.
Thank you.
Yeah. No. Actually, I do the opposite. I only rotate the orbital degrees, and I don't rotate neither tau nor spin. The reason why I do that is because I was hiding this a little bit but the reason why I do this is I want that the basis states are the same, so that when I do here, not only I look at the mass, but I also look at what is the ground state for here, the ground state with this edge state and the ground state here, and I need to make sure that they have the same character, so that they have the largest orbital overlap. And so in order to do this, I want that when I write a 4x4 matrix, so when I write, so I can write this as a 4x4 by explicitly explaining what the basis states are. And I want that this plus and up always mean the same thing for each alpha. So that's why I don't rotate in the tau subspace and in the sigma subspace. Otherwise, I could be misled in thinking that I have a gap inversion, but in reality, it's always the same, always the same type of state that is the low energy. So I was hiding this a little bit, because basically what we do is, from when I diagonalize this, I can write the lowest state in terms of the plus and minus, and then I can check that if I have two edges, I have the largest overlap between the two grounds, either between the two ground state or the ground state and the excited state. So if I have between the two ground states, then I don't have an inversion. But if I have between, so if we, on the other hand, if I have between one ground state and so there is a little bit hidden. So I told the story in the simplest way with the mass, but of course, it depends on how you order the states, and in order, whether you have mass inversion or not. And so I needed to keep track of that. So I hope I answered your question.
That's the effective magnetic acting on a basis which is not the spin basis, but which is a combination of
No, if the Hamiltonian, no, because we never rotate there. So it's actually, no, if the Hamiltonian is this, where is it? If the Hamiltonian is this, it's actually acting on a spin basis, because you see it goes as tau zero. Now the question is how you realize this model. And so, because in principle, if you are not adding a magnetic field, you could sort of find a material that somehow has that model, or something that is unitary equivalent. But that's now, if you do a unitary transformation that affects sigma, then the magnetic field might become something complicated. But so the way it's written, this would be a magnetic field.
Thank Michele. Great talk.
Thank you guys for your attention.
How to check it. If it's not much out there, I'll go and chase it up, but there should be some.
Shall I stop?
Yeah, I guess.
I guess we can.
Bye, everybody.
Bye.